Alright, hello. This is my video for today's quiz, which is quiz number 7, and we're looking at chapter 17. And in this problem we're given a disk with a radius r, and there's a wire wrapped around it, and we're asked to find the velocity of the center of the disk as it moves down a distance of s. And so we weren't given any numbers, but we were asked to find an equation that will help us find the velocity of the center of the disk in terms of some of the given variables in the problem. And so looking at this problem, I noticed that we were relating a distance to a velocity, and so I decided to use our work energy principles from the beginning of chapter 17. And so I drew a free body diagram here and labeled some of the things we were given in the problem. So I decided to call the center of our disk G, and then we were told this radius is lowercase r, and then we have the velocity of the center G downward, and then we have an omega term because of the wire that's wrapped around it. And so the next thing I did was write out the equation for work energy here. So we have the kinetic energy plus the potential energy before has to equal the kinetic energy plus the potential energy after. And in the problem we were told that the kinetic energy would be 0 because it starts at rest, and so it only has potential energy from the height because there's no springs. And then afterward I decided to set my distance at the bottom equal to 0, and so once this reaches our distance s that we're interested in, there'll be no more potential energy, but we will have kinetic energy. And so these are the two equations we have for our potential and kinetic energy that don't cancel out and equal 0, and so we have this is basically mgh, except in the problem we were told it was moved a distance downward s, and so we replaced the h with an s. And then our kinetic energy here, we have two terms. We have our translational term and our rotational term, and so this part is what's new to chapter 17 since we're looking at rigid bodies. And then this term here we can plug in some of our known equations, because we know the I value for a disk is 1/2 mr squared, and then we know omega from our kinematics has to equal velocity over our radius, and so we can plug both of those terms in and then take these two terms here and plug them into our work energy relationship here. And so that's what I've done here. It gives us this equation, and then it's just a matter of trying to simplify this and see what cancels out. And so this actually simplified really nicely. There was a mass term in each term, and so the masses would cancel. The radius squared in the numerator here canceled with the radius squared in the denominator here, which gives us just this. And then since these are the same term, we can add those together to get 3/4 vg velocity of the center of the disk squared equals gravity times s. And then from there we want this in terms of our velocity, and so we can multiply by 4, divide by 3, and then take the square root of that to get our final answer here of the velocity of the center of the circle as it moved downward a distance s will be the square root of 4/3 gravity times s. And so that is the answer for this question, and it will also be in the downward direction. So thanks for watching.